Okay, so let's get started. Thanks everyone for joining. Today it's our great pleasure to have Professor Fei Miao to share her research with us. Professor Fei Miao is currently a Pratt & Whitney Associate Professor of University of Connecticut, where she joined in 2017. Sorry. And she got her PhD and postdoc from Grass Lab of UPenn. She received the NSF Career Award along with many other NSF awards. That is amazing. And also she's the recipient of many Best Paper awards. Yeah, and her research interest lies in the multi-agent reinforcement learning, robust optimization, uncertainty quantification, and game theory. And today she's going to share with us about their work on the learning and control for multi-agent systems. Without further ado, let's welcome Professor Miao.
Thank you for the introduction, and thank you for inviting me here. So today I will mainly talk about our work on learning and control for safety, efficiency, and the resiliency of embodied AI. So with the development of AI technologies, we can have a lot of opportunities in providing like real-time predictions, and also based on, for example, reinforcement learning, we can do better actions, and hopefully in the future we will have better systems in many like robotics fields. And especially our group's work, we are interested in multi-agent systems, the learning and control side, because we do see this is a growing market, no matter it is autonomous vehicles providing transportation service as a kind of intelligent transportation system, or it's a warehouse robot with different heterogeneous robots collaboration. And we do see there are a lot of growing opportunities. However, there are also many challenges for the current existing systems. So if it's just, for example, train a reinforcement learning algorithm in a simulator or playing a video game, then it's okay, the system failed and we just restart the game. If it's a real robot, we really don't want to take the risk, and especially if it's, for example, autonomous vehicle carrying people, no matter if it's a single vehicle accident or it's like a chaotic transportation system, we hope we can improve the safety and the efficiency of the system in the future. So to solve these above challenges, my research can be categorized in these three main fields. So the first one is our focus today, learning and control with communication for multi-agent system. And I will only briefly introduce our work on data-driven robust optimization and CPS security. So for learning and control, traditionally, people have a lot of nice work focused on, for example, a single agent system. And we found out that actually communication idea exists. For example, for connected vehicle, maybe back to 30 years ago, there have already been ideas if vehicle can talk with vehicle or vehicle can communicate with road infrastructure. Basically, they can coordinate, get more information, and do better decisions. Basically, the opportunities here we can leverage includes we get ubiquitous sensor and actuator capabilities. And the environment we consider is a data-rich environment. It means that we can access no matter historical data or real-time streaming data. And we assuming we can have communication capability and some sort of computation capability. So even with these opportunities, there are still a lot of remaining challenges. So first, we want to tackle usually this system, considering the multi-agent setting, it's a complex dynamic system. Means it's hard to assume that we can model the full dynamics of the entire system, no matter it's like very large, high dimensional, or just assume we know exactly the dynamics considering the interactions of these systems. So those are hard assumptions to really hold in reality. So here, basically, we need to consider the complex dynamics of the system, and we can't assume we have the full dynamics model. And we have to consider, based on the data, maybe we can learn some knowledge about the system states, but there can be a lot of uncertainties. And also for these kind of physical dynamic systems, we have requirements about safety. Hopefully we can satisfy these safety requirements and make a decision for this large scale system. And finally, we also want to ask the question, say, is communication really necessary here? Since there has also been a lot of literature about, say, fully distributed decision-making, agents don't communicate, or communication is very restricted, the resource is not available. We want to define the problem as if considering environment like a ground transportation or in a warehouse environment, so communication has some capability, and then under that scenarios, is there any benefit if we bring in communication in the learning and control process? And basically, the foundation of problem we want to understand is the tridirectional relationship among communication, learning, and control. So now we utilize this kind of intelligent transportation system as an example. Specifically, the kind of traditional loop we want to consider here is like if we have autonomous vehicles and the vehicles can communicate with each other or can talk with road infrastructure. Basically here, through the sensing stage, there can already be communication. They can maybe share some of their data, and then, for example, through the computer vision stage, they can do co-perception, collaborative perception, basically. And then with some computer vision knowledge, we want to make decisions for these vehicles. And then the questions here is a current technology really say full stack autonomy, every part is really well integrated, or there are still some gaps? And our answer here is we do think there are currently gaps. And for the first part of the talk, we will introduce our recent work on uncertainty quantification of collaborative perception, and then we will introduce our work on safe and scalable multi-agent reinforcement learning with communication technology. And we want to quantify the benefits of communication and reward reallocation to incentive agents to coordinate. And finally, we want to talk about our theoretical and algorithm design work on robust MARL under state uncertainties. So let's start from UQ of collaborative perception. So computer vision has been a very hot research field in the recent years, especially with the developing of deep learning methods. And collaborative perception has also been a very recent hot area that even multi-agent system has been like analyzed in control and planning fields for a while. Perception people, recent years, they noticed that, oh, maybe perception side, there can be a lot of collaboration. And they have designed methods like what is called early fusion. Basically, they share raw data, and then every agent will have a large amount of data, and it has neural network capability to do, for example, object detection and tracking, etc. And there have also been work like they call share intermediate feature. Instead of sharing the raw data, which costs a lot of communication and computation power, they only share intermediate feature after every agent processes the raw data with several layers of neural network, and then utilize a feature to design method to do object detection, for example. And there's also like a late fusion, only share, for example, the final bounding box object detection result, and see how can that shared information improve the detection. And meanwhile, the field of uncertainty quantification has also being developed with fundamental methods like Monte Carlo dropout, deep ensemble, etc. But the drawback of these methods is they are okay for maybe doing detection or classification for like just static pictures. But for this sort of a dynamic environment, a moving environment, if we need real-time fast computation, they are not good for inference stage calculation. And other methods like direct modeling, which called like during the inference stage, just learn the uncertainty. So it's over-optimistic. So that cannot really capture all these complicated cases in the real world. And our motivation of really started doing this uncertainty quantification is if they see the right figure, like for path planning and control, people say for the bounding box, if, for example, if the ground truth is a green and our prediction is a red, right? And if we use the red to do path planning, it's likely that we will have collision with the obstacle. And for robust path planning, robust control, it's like even we don't have a ground truth prediction. If we have some uncertainty set that tell me, say, my prediction might have some uncertainty, and I can use maybe a larger bounding box to represent my prediction result, then we still have some hope to keep our path plan and control decision safe. This is our motivation. And we searched the literature and we found out that even for this kind of very naive thoughts and very naive requirement on the UQ part, there is no existing perception literature really give us this sort of a calculation procedure. And basically, we design UQ process for collaborative object detection that can provide us this sort of inference time UQ. And later we will show that actually considering UQ can have two kinds of benefits. Of course, we will reduce the uncertainty when we consider that as a metric. And surprisingly, that also helps improve accuracy of the detection result. And the methodology here mainly includes two parts. So the first part is through the training stage that we will utilize the literature of direct modeling that for the neural network structure, no matter it's sharing intermediate feature or sharing like early raw sensing data or sharing just the post-processing detection result. Basically, instead of only care about like the prediction of the mean, we also care about the covariance about the prediction of location of each vertex of the bounding box, and adding that covariance as one output in the neural network part. In the loss function part, the loss function includes basically reducing the KL divergence style of loss instead of only care about accuracy. And then remember we talked about that direct modeling can be over-optimistic estimation. And here we also have a calibration process based on moving block bootstrap that basically we separate the data set as several folds of training and validation, and just resample the data, retrain it, and then validate it to calculate its coherence on this validation data set. And later we will use the average of covariance as the validation covariance. And finally, during inference stage, we will add up both this direct modeling part of covariance with the calibrated bootstrap-based covariance as our final covariance matrix.
Sorry, just have a clarification question. The sigma is a function of state, right? Sigma is depends on sigma is a neural network. The input is the the covariance matrix. Sigma hat, sorry.
Sigma hat. The result is it's just a covariance matrix.
So the input of
the input is a state. The input is
the history of state or just the.
So here we didn't use any history yet. So the input is like the neural network part,
Gotcha.
just like the vision part.
So same input as the detection.
Yeah, as a deep learning detection.
Gotcha.
Yeah.
Yes.
And the kind of result of this UQ is basically, originally if you don't have UQ, like every second we have, for example, 20 frames of object detection result. And now it's like through the inference stage, we will also output the UQ. It shows as an ellipsoid, orange ellipsoid. So basically that's every vertex has an ellipsoid to represent the uncertainty about its location prediction. And for example, the first video compares what is called DiscoNet and upper bound. Basically, DiscoNet is one collaborative perception method only sharing the intermediate feature, and upper bound is sharing all the raw data. And we can see that their uncertainty looks similar, and the lower video compares what is called DiscoNet with lower bound, and lower bound only shares the final detection result, the final bounding box. And we can see that this lower bound method has much larger uncertainty because orange ellipsoid, the area is pretty large. And we also have this table result to show more detail for comparing metrics. So every row in, for example, the first table, every row represents a different kind of UQ method, and the left row is our method, and the first the first three rows are without any UQ at all, or only depend on direct modeling, or only depend on bootstrap. So this is kind of evaluation study, and we can find out that basically, in sharing intermediate feature style of collaborative perception and sharing upper bound, sharing all the raw data collaborative perception, our method always has basically the best accuracy performance. And it's interesting that actually in sharing intermediate feature and sharing all the raw data, we can improve the accuracy of object detection result. Instead of, say, originally we thought maybe if we care about uncertainty, there can be a trade-off between uncertainty and accuracy of the prediction model. But it turns out if you care about uncertainty, it also improves accuracy, which is like a good sign. And the second table shows basically UQ evaluation, and usually people use NLL as a metric. It's smaller, the better. And basically, our method has the best UQ performance in different kind of collaborative perception model. And also compared with the baseline, we can reduce the uncertainty a lot, basically up to 4 times of reduction. And some insight here is first, communication and collaborative perception actually helps improve object detection accuracy. And also it helps to reduce uncertainty. And a second insight is uncertainty quantification actually can also help us in deciding sharing what kind of information is good. So for example, communicate intermediate feature. If we only care about accuracy, we can see that sharing intermediate feature accuracy is smaller than sharing all the raw data. But if we compare uncertainty, sharing intermediate features actually has a smaller uncertainty. So which means this can be a metric to evaluate maybe under different situations. We can choose the appropriate amount of information to share among agents. So that's the first part, UQ for object detection.
For the previous slides, when we see the second row, if you play the video, there's a vehicle on the right that is blinking. And so, this one, like what is happening here?
So, so this part only shows the detection, not show the tracking. So one reason can be that on different frames, some object can be, for example, there can be a occurrence. So it's like at some frames there is an object there, but it doesn't clearly show the detection. Yeah.
I see. But whenever we see that, we can do this uncertainty quantification and then calculate that.
In this paper, we didn't specifically talk about the occlusion issue yet, but we also have one under review on RAL. So that's about object tracking, and there we talked about how we can utilize this UQ information in the detection stage to improve the tracking result, and we can show that if we include UQ information, it can help on some objects, maybe there is a occlusion issue in some frames. Yeah.
Okay. Cool. Thanks.
A quick question, what does the blue lines mean?
You mean this sort
blue
of
circles.
radio circle?
Yeah.
These are the point cloud, the LiDAR point cloud data.
So
yeah, that's just like the original, the raw data, and then the bounding box shows like based on the raw data, the detection result.
So your input is not RGB images.
In this paper, we don't include RGB. We only use point cloud LiDAR data.
Okay,
yeah.
Is this a data set or a simulation platform?
Currently, because here we specifically want to study the effect on collaborative perception. It's only simulated data, and I think our collaborator work on collaborative perception, they are collecting like real world data. Yeah, usually if a single vehicle object detection, there can be a lot of real world data. Collaborative perception, not that lot yet. Yeah.
Thank you.
Yeah. And then we want to see on the decision-making part how we can do better coordination scheme considering all these safety constraints and also improve the system's efficiency for multi-agent system. And specifically here, we want to focus on safe and efficient multi-agent reinforcement learning. So why reinforcement learning instead of maybe traditional model-based control? As we already explained, we don't want to assume here that we know the full dynamics of all the agents considering their interactions. That can be a very strong assumption. So the decision part can also be in a hierarchical structure in the sense that every agent has decision considering how they interact with the other agents. For example, in this connected autonomous driving scenario, every autonomous vehicle needs to decide at the current procedure, should I keep lane or change lane if I want to reach some destination point? And also, the decision includes dynamic control part. Say, every agent can only assume I know my own for like this sort of dynamics, for example, like a bicycle model, and I need to decide like the continuous control input, like steering angle, throttle, this sort of thing. Yeah. And basically, the decision part can include both MARL learning-based decision and also this control on the physical dynamics space. So. The current literature or the current popular framework of MARL usually assume that in the training stage, agents want to have some knowledge about what other agents will do at the specific state, and then get the reward from the environment to tell the agent at a different state, if I do some specific action, what can I get? So basically, the structure is a centralized training and decentralized execution structure. And the issue here is, even in the training stage, TU can have this curse of dimensionality if we really have a joint global state and action. And then the question here is, no matter it's centralized training or decentralized execution, or it's fully, for example, localized policy. Fully localized policy has, again, the issue of POM-DP itself is already like hard to prove, and then if it's a multi-agent system, decentralized POM-DP, then the agent will lose too much information. It's hard to say what guarantee you can have on the policy. And another issue is considering the safety constraints, and recent years there has also been literature about safe RL, and I also see Changlia has a survey paper about that part. And so usually methodologies can be described to these different categories. So for example, there can be defining safety constraints for the RL process through maybe temporal logic perspective, or through like a constraint MPP. And it's hard to really just using one constraint function to represent all these complicated safety constraints through the entire sequential decision-making process for the robot. So that might not be a good solution for safe RL or safe MARL considering this multi-agent setting. And for single-agent RL, it does not straightforward generalize to moral safety requirements and safety constraints. So we still need to redesign the safe moral algorithm. And also there can be a method like project the action back to the safe action space if the explored action by RL is not safe. But that can interrupt the learning process. And our question here is, we care about safety and the scalability of the MARL algorithm, and also we want to rethink about a fully centralized or fully localized policy. If we have communication capability, how we can utilize this part of information. And our first design is assuming that in the training stage, agent can share their state and the action pair, and basically then every agent, the Q function they can train is a QI that with the state, joint state and action information from the uncapable neighbors. And for example, we can decide which neighbor agents we can communicate according to maybe their distance or according to their connection relationship on a graph, etc. So we don't need to, we don't specify it in this work, but just assume we can communicate with a subset of the agents instead of not the entire group. And then the queue function we can get is what we call a truncated queue, only with this sort of communicated agents as an SA pair. And we can prove that compared with the centralized optimal QI, the error can be bounded if we only have like a subset of SA pairs. This is the first part. So assuming agents, they can share their state action information and whether we can utilize it to train the queue function part. And then the second part is about the safety constraints. So here, because it's hard to say every agent has information of the entire system, basically everyone cares about safety of itself. So for example, in a driving scenario, it's like every agent has its own dynamic information and only has information of the other agents through the computer vision observation part. For example, I don't know the human driver's fully dynamics, but I know its current location or velocity, etc. And we assume, for example, safety requirement can be no collision and keep a safe distance with the surrounding agents. And in, for example, lane keeping and lane changing scenarios, we can write different types of barrier function. And then the safety checking part is every time if RL through the exploration process explore some action like a keeping lane, and then we utilize this barrier function to check whether keeping lane can have some continuous level safe control input. If there exists safe control input, then we know, okay, at the current stage, keeping lane is a safe action, and then basically we feed back this safe action to the RL part as a pair in the training buffer. And then through this sort of safety checking for every agent, we can show that if our safety requirement is about no collision or collision avoidance, and every agent checks its own safety through the process of training and execution, then we can make sure that there is, if every agent keeps safe, then basically the entire system keeps safe, like no collision.
Sorry, I have a question. So here, are you assuming the dynamics of the FIG doesn't depend on neighbors? So the dynamics of each car only depends on itself? So their interactions mostly from reward, right? Their reward is the kind of difference.
Yes, the MARL part takes care about the interaction, and for the safety checking part, dynamics is only itself.
There are different levels.
Yeah, and also we don't need to know the other agents' dynamics, but we assume we have information about, for example, position, and then we can set up if the safety distance is a specific value, then we can write this H function in the safety checking part.
Gotcha, thanks.
Yeah.
And another quick question, like if you go back to previous slides, just very curious. Sorry, the RL part, theorem one. Could you comment on what is gamma and kappa? Especially like gamma, like
yeah, gamma is the discounted factor of the RL part. Yes, and kappa is the, for example, number of hops of neighbors. So if we can communicate with one hop neighbor or two hop neighbors, it's like if kappa is large, then basically means the agent has a larger amount of the other agent's state and action information.
And this Q is Q star, right? It's optimal.
Yeah, it
Gotcha.
means optimal here.
Thanks.
Yeah.
So here we use computation here for improvisation. Right? So I guess what if there is a communication error?
Communication error.
Yeah.
Yes. So for the first part of the first step, we just assume communication part no error, and later we indeed have MAR, robust MAR considering, for example, state uncertainty or error. Yes. Yeah.
What about interrupted communication?
Oh, interrupted communication. So again, here we just as a start point. And currently we are working on, see if it's interrupted communication. It's like there can be packet drop with some probability. For example, maybe Bernoulli distribution style of packet drop, and that part can be defined as the reward part. If packet drop, then our reward is like no communication, and if perfect communication, then we can define another reward function example. So we are working on like MARL like that. Yeah. And here we run experiments and validation of algorithm in color. And basically we first show with information, with safe action mapping or without safe action mapping in a multi-agent setting, what can happen. Basically, without safe action mapping, the car can have a lot of like collision actions. If we train, for example, 10 or 30 agents together in color, and it's really hard to make the model to really like learn some good action. And then we compare, say, if these cars, they can really coordinate when there is all like autonomous vehicle, and when on streets there are some other vehicles, like a human driving vehicles, and see the traffic efficiency in different percentage of autonomous vehicle. Yeah, so here, basically the blue vehicles are human driving. So here, just in color, it randomly simulates some car speed or anything. We don't control it at all. And just to see our trained MARL agents, can they react smoothly to these human driving vehicles? And it turns out it's okay, as long as those blue cars are not doing crazy behaviors. And we also want to show whether communication can improve the efficiency of the system, especially in some special scenario. Like here, basically it's like vision is blocked. So if there is some accident at the corner, for the vehicles, if no communication before they reach the corner, they cannot see that actually, and they will form a traffic jam. But here, we simulate, say, they can communicate, they share information, and the following car has information like the speed of the vehicle already gets slow, and the optimal policy will be like a change to a faster lane, and then they will avoid the traffic scenario at the corner part. So basically, we show, for example, the improvement on system efficiency, like average velocity or average comfort, when they have different percentage of CVs on streets. And of course, if 100% CV, then it's good because they just follow the algorithm and or coordinate. But still, if we have some percentage of CVVs, like mix human drivers, then still we can improve if they coordinate compared with algorithm, not considering, say, sharing information or coordinate at all.
So in the, I think a couple of slides back in the video where the autonomous vehicle like just stopped in between when like the human driver was changing its lane in front of it. Like, does the car have knowledge about all the agents or like only the autonomous agents? Because then like I think a blue car was approaching from behind it, and like realistically speaking, like if a car just stops in between, even like due to some other car's lane change, like it's unsafe for the car behind us, like it can bump right into us, right? So like, does it have that perception knowledge or?
It can be different assumptions. So, for example, the video here first said we just assume auto cars, they can share all their available information, they share their own speed velocity, and they share what they observe based on their own vision with the surrounding agents. Yeah.
Okay.
And later we will show something more relevant to you, to your question, is about like a safety critical part.
I have another question. You
Sure.
mentioned that as long as the blue drivers do not do crazy stuff,
Yes.
and they also get a safety guarantee. So I'm wondering what assumptions do you have for the blue cars?
Yeah, so for example, for blue cars, our assumption is, for example, we only know its current position, and if we have good LiDAR sensors, then we can also estimate its velocity, right? So then when we generate those like environmental vehicles, basically it's like following the assumption, say speed has range and position error has range, etc. Yeah. So it's like follow some specific distribution. Yeah. And later we will also show if they don't, what will happen.
Okay.
Yeah.
Thank you.
And here's just some figures showing on the safety part. So again, it's like if the blue vehicles, basically it's like our knowledge is kind of the same distribution with their real behavior, then we can have safety guarantee. Basically, if the distance is positive value, then it means we don't have collision. And we also compare the unsafe actions avoided under different traffic density if we have this safe action mapping module. And if we then compare the reward, so in a multi-agent setting, especially because there are many vehicles on the streets, there are agents, there are other vehicles. So with this safe action mapping, we can avoid unnecessary collisions during the training stage. Then this episode can continue to train. So the reward can also improve much faster than without a safe action module. Yeah. And now the question is, so if human drivers are doing like just the normal behavior as our expectation, then everything is fine. But what if they do something abnormal? So it's like if somebody is even running in the red, so like, oh, for example, in stop sign, someone just rushed out, right? So it can be kind of very dangerous. And also there can be behaviors like just suddenly park on the highway, we have no idea what is happening, right? So if the CVs, they don't really share information, they don't coordinate, even one vehicle who sees this kind of behavior avoid collision, and for the following vehicles, it can still be very dangerous. And our question here is, can we design better, safe moral algorithm in these challenging scenarios that make sure that these CVs, they coordinately improve the safety rate of the system? And here we have two main design module. The first part is to better react to what is happening. They must have better knowledge to understand what is happening. So just a normal, maybe fully connected neural network really cannot do that. Here we design a GCN transformer structure. Basically, the CVs, they can understand in a graph manner that their connection with the surrounding vehicles, no matter it's other agents or it's a human driving vehicle and the surrounding with like a road segment or boundaries of the lanes, etc. So representing that information in a graph structure. And also, we need the transformer encoder. We can input a history of the surrounding agents, and through the state of the history of the state, actually we can better understand what the agent is doing. Is it like just a normal driver, or the state change abnormally, and sort of information to give the agent to better understanding the surrounding environment. And the second module is we need a stronger safety shield, especially for those abnormal scenarios and when the other surrounding environment agents is doing something crazy. So for example, the safety shield we designed here is not just a linear barrier function at all anymore. So here we have a second order information, and we need to consider, for example, keeping safe distance with vehicles on the current lane, and also we need to consider if the auto car want to change to another lane, any potential surrounding vehicles might also change to the same lane. We want to keep the safe distance. And then the barrier function part, the second order information about the velocity part also helps to better understand maybe some vehicles are doing really fast, like acceleration, deceleration, so that's sort of the information. So with a stronger safety shield, and again, we check every action of the auto car or of the agent and see if there exists feasible, safe, continuous action. That means at this step, okay, changing lane can be a safe action. And we will get this part of safe action to saved in the training replay buffer, and unsafe action can generate negative feedback to the critic part, and then we can see with both better understanding of what is happening and also stronger safety shield under these like dangerous scenarios, we can indeed improve the safety rate compared with method like this strong safety checking module. And of course, improved safety can also improve the efficiency, right? So if you have an accident and you park there, and indeed, like it will slow down also the following vehicles.
Quick question. Can I interpret it as the proposed method is like essentially considered a second order system rather than the red one considered first order system? So you're doing some reasoning in the acceleration level.
Yes.
Is why you can react before it happens. Like,
yeah,
does that make sense?
Yeah,
I know it's not exact, but roughly.
Roughly it's like considering potential. Yeah, exactly. For example, like this later, like for example, especially like this scenario is suddenly parked on the highway. I see. Considering basically potential acceleration, deceleration, and then that helps improve the safety rate significantly. Yeah.
I see. Thanks.
Yeah.
So in these cases, like what happens if the autonomous vehicle has taken decision to avoid the human vehicle which is doing abnormal things, and then like within the same time like the human decides to like realizes that he's doing something wrong, and for example in this case it can try to change its lane because it sees cars coming behind, and then basically all three are in the same lane again, right?
You mean say suddenly changing lane, not suddenly.
Yeah, because like human is thinking that they are taking a safe decision by changing the lane, whereas the autonomous vehicle is thinking it's changing lanes to have a safe passage.
So we did not specifically testing that scenario yet, but actually, that is like a vehicle should not run on that specific lane, but some vehicle occurs. If we have that sort of example in the testing, maybe it can improve the safety rate, because like here when vehicle run in the red is similar. So it's like if in normal case there shouldn't be this sort of vehicle on the lanes auto cars are driving. Yeah, so they're pretty similar. Yeah. Even if, for example, we train these agents, and in the testing environment, we change, for example, the number of environment vehicles and the number of connecting vehicles, cooperating agents. So still the neural network can work because decent transformer structure-wise, it can take like the training number of agents, and then we test it in different numbers. Still, we can improve the safety rate and also the efficiency of the entire system. And of course, we want to see if we really push the boundary of the agents in the training stage, and we just testing it in like a very normal driving scenario, can it react very well? And indeed, if in the testing stage we only use like again normally behavior agents, the safety rate can be like 100%. Yeah, so it's not like overfitting style of training. Yeah. And then the question is, so if the agency can coordinate, then it's good. But just assuming every agent wants to coordinate may not be the full story, right? So in some cases, for example, a lot of coordinated game just assume we set up an identical reward function for every agent, or we just assume every agent, the objective is optimize the total system reward, and then the algorithm works fine. But for many scenarios, actually, if one agent wants to optimize the system level reward, it sacrifices its own benefit. Like in this scenario, okay, so if this vehicle C wants to change to a faster lane, if D coordinate, then it needs to yield a little bit. But actually, if D doesn't want to coordinate and just runs very fast and doesn't care about the system level efficiency at all, that can be a potential behavior of an agent, right? So then the question is, if we can redistribute it, the reward of the system back to maybe agent D, like contributor to the system, and then it can be an incentive to motivate agent to really coordinate. And our methodology here is we found out the idea from a classical game theory. Shapley value is a very useful mechanism to measure the contribution of each individual agent in a cooperative game. And the literature is in a static game setting, like tabular case, and we generalize it to the MARL case, say through the training process at a different training procedure with like the sampling, the assay pair. We define the critic as the Shapley value style that basically the critic measures the marginal contribution of every agent to different collisions. So it's like if the agent tries to coordinate with the other agents, or it chooses to not coordinate, what will be the change of the total reward of the entire correlation, and that improvement part is like this single agent's contribution. And we utilize this define as the critic function instead of just using a Q value function. And we can show that if we define this Shapley value based critic as the critic in the expert critic algorithm for MARL, and we can show that this is an efficient reward reallocation scheme in the sense that the system's total reward is completely distributed to every agent for cooperative policy learning. And it is also a stable reward reallocation if the game satisfies a convex game condition that all agents will stay within the collision, communicate, and cooperate to optimize the objective, the system level objective. And we ran some experiments and evaluation in, again, a CV setting, and we show that compared with just giving every agent identical reward function, if we utilize this Shapley value-based critic, we can improve the entire system's basically reward again. So I think this can be generalizable reward reallocation scheme to different multi-agent system setting to help us rethinking like what can be a real coordinate game instead of just a set identical reward function for all the agents. And then the final part, we would like to introduce our work on robust MARL under state perturbations or under state uncertainties. So there has been a significant effort on robust and reinforcement learning, considering, for example, simulation to reality gap, the state transition uncertainty, like defining a transition kernel, etc. However, that isn't the full story of considering what can affect the policy or affect the performance of the system. So think about robotics. No matter it's autonomous driving cars or manipulations or drones, etc. So a lot of state information for the decision-making part, for the action part, actually comes from the computer vision information, and it's hard to say that part is 100% accurate information, especially in a multi-agent setting. If every agent has a small perturbation on their state part, then the distributed policy can have a lot of like bad behaviors, even unsafe actions. And then the question is, if there is state perturbation or state uncertainty for a MARL, for a Markov game, basically, then what can be a good algorithm and what can be a good solution? So our first attempt is theoretical analysis. And the setting is we model state uncertainty, state perturbation as some adversarial agents selecting how to perturb the state of every agent to some other state. And we just assume after perturbation, it is still within the state space, but it can be like a wrong or different state. And then the Nash equilibrium concept is defined as what we call a robust equilibrium. Means that every system agent only has the perturbed state information, and every adversarial agent has the correct state information, but the action of adversary is the selecting like a perturbed state to play in this sort of a game, and adversary just want to minimize the reward of the system. And then we found out that under various specific conditions. So for example, if the state perturbation function or state perturbation policy chosen by the adversarial is a bijection function, then for a finite state and action game setting, basically tabular game setting, we can still prove that the robust equilibrium exists. And we also design algorithm like a tabular case Q-learning algorithm, and we can show that the convergence of that Q function. However, this sort of perturbation function is a bijection. That's kind of a really strong condition. And if no that sort of condition, the robust equilibrium won't hold. And our best hope is basically the agent, the adversary can perturb the state to any arbitrary state as long as it still belongs to the state space. And we can only do, say, maximize the worst case reward is kind of solving some max-min problem. And remember here, the special part is the adversarial state perturbation. Adversarial has the true state information, but the system agent does not have. And we also design algorithms like gradient descent ascent. Basically, there is adversarial in the training. Adversarial wants to minimize the system reward, and the system maximize system reward. And in MPE, the very basic particle environment, we can show that if we consider in potential state uncertainty during training stage, and then in testing stage, we use different style of perturbation, no matter noise or well-trained adversarial, we can always get better mean absolute reward. And then the last part is, so for particle game, it works well. What if it's an autonomous system, it's a robot, it has physical dynamics, not just a particle setting. And the state error, as we show that if the other agents not really have a correct state information, then it can have collisions, it can have unsafe actions. And this paper is still under review, and we put it on archive. Our design here is we need to considering safety and robustness as basically a coupled question. So we design what is called safe and robust MARL algorithm under state uncertainties. And the main algorithm part includes in MARL part, we don't have adversary in the training anymore. So we put worst case Q as a regularization term through the training process. And then the MAPBO will take this sort of regularized Q function as a critic instead of just using the common Q function. And in the safety shield module part, we model the system dynamics error as a kind of error on the state part, and then utilizing the robust CDF function as the safety checking part. And of course, if the action is safe, then it is saved in the replay buffer as a training example. And if it's unsafe, we will feedback a negative reward, a penalty to the system as a kind of learning procedure. Say this state action pair is unsafe. And we tested this algorithm in, again, different different scenarios like intersection or highway, and give different styles of perturbation, like just a random noise perturbation or a very large number of perturbation on the targeted vehicle's location and velocity. And we show that safe and robust MARL can improve the safety rate. And of course, here we don't have 100% guarantee because we cannot know the accurate state information of the surrounding agents, because here we can only assume we know the range of the uncertainty set, but we don't know the exact number of the location or velocity at all. So, but still, as long as we consider robustness design potential error, it is better than not considering robust safety shield. We did some evaluation study, including only put robustness on the MARL algorithm part, but with a normal safety shield, or no robustness algorithm on the MARL part and put a robust safety shield, etc. So we did evaluation study, and it shows basically considering state perturbation in both the MARL algorithm part and the safety shield part has the best performance. Yeah, so I think I can put my summary here or conclusion here, that through our study we found out that communication can help for improving collaborative perception performance, that it improves both object detection accuracy and can reduce the uncertainty. And also, when we studied uncertainty quantification method, we found out it can also inspire the communication part, that sharing intermediate feature can perform better in terms of uncertainty reduction compared with just communicating the raw data. And through the learning and control methodology design, we also show that communication can improve the safety and efficiency of the system in both normal scenarios and very challenging scenarios, like surrounding objects have unexpected behaviors. And we also believe that UQ can bridge the gap between the perception part and the action decision part in the future. And finally, we want to say, considering robustness is important for multi-agent systems and also important for MARL methodology design. And safety and robustness, they are coupled questions, and to really improve the safety of the system, we need to consider robustness. And here are my PhD students, and some of them are already graduate and some are graduating recently. And in terms of hardware, so currently we have like every single vehicle can run in the track, and we are working on the multi-agent demonstration. Yeah, so I think I can just stop here and welcome for more questions.
Did you use, for worst case Q network, did you use state calls as a state R?
The worst case Q part, that is for considering like you might have a state error in learning the Q function. So that part is not specifically for safety issue. Yeah. So safety module, that's another part. But of course, we do have safety as a feedback to the system. So for example, if there is unsafe action, it gets a penalty, and then basically that part of reward will enter like the next iteration of training the Q function. Yeah.
Yeah, I have a question. So for a lot of the cases where the collision rate or collision-free rate is not 100%, what is happening in those collision situations? Is it that the vehicle dynamics is not following your assumption in designing CPS?
The main reason is we don't assume we have exact information about like the location or velocity of the surrounding agents. Yeah. So we only assume we know, for example, the dynamics of our own. So if the agent is autonomous vehicle, then in the simulation we just basically use bicycle model to simulate the dynamics. But for the surrounding vehicles, when especially in those like dangerous behavior, we just randomly generate its speed and it can do like a very fast acceleration, fast deceleration. We don't assume we know like the exactly what is acceleration, deceleration range, etc. So the main reason is we don't know its exact state information. Yeah.
I see. But if you can assume a bound for their like acceleration or velocity and then use that bound in your CDF, do you think you'll achieve 100% collision avoidance?
So if we exactly set, say, in the CDF, the safety shield, the bound or the H function is considering maybe this amount of error, and then in the testing environment we use exactly like that kind of bound to generate the surrounding environment's agent's behavior. For that part, then it can pass the testing. It will keep safe. But if we say in the safety shield we don't assume we use exactly the correct information, then it can still have accident. Yeah.
So the major issue is the
mismatch on information set. Yeah. So but still, even there is mismatch, as long as we consider like a robust safety shield, still we have some hope to improve the safety rate. Yeah.
Sorry, like how much of it is from the control actuation limit? Because CPF doesn't basically assume unbounded control action. So like either some failure case from the unbounded control space assumption. Just curious.
You mean the...
To solve the QP, right?
Yeah,
it actually need to assume U is unbounded, but in reality, U is bounded. And just,
so I think in our case, we assume that the U is bounded in the sense that like a throttle or acceleration, it only has specific range. Yeah, especially in simulation, it cannot be like an unbounded large. Yeah, so it has a range.
Yeah.
And also another way is doing the MARL design. So for example, the action set. Let me show. For example, in this sort of safe MARL in challenging scenarios. So we didn't talk about the detail of how we define the action set in MARL. So actually, if you check the paper, our action set is defined as discretized controller input. So it's like we choose to keep lane with certain speed, or keep lane with acceleration or throttle within several, maybe 5 discretized space. And later the control part, the input U will be consistent with this action, the discretized space. Yeah, we have some sort of design.
Thanks. Yeah, thanks.
Okay, and so we're slightly over. If there's any quick question, we can do it. If not,
how much does the size of the graph affect the whole in process? The number of agents, different kind of like maybe pedestrians or all that does increase the graph exponentially.
It depends on the number of, basically the number of agents that AI or agent I is directly like interacting with. So for example, if it communicate with one top neighbor, then basically like the closest surrounding auto cars and also the other surrounding environment object it can observe. Yeah, so that's why we say basically it's a scalable algorithm design. So like the state information of every agent, it does not include the full environment. It only includes like within its own observation what it has. Yeah, but of course, if we say one agent can sharing, for example, 3 or 5 other agents share the state information with it, then it has like an enhanced state information. Yeah.
Okay, thanks.
Okay, let's thank the speaker again.